Namaste dear learners. Today we are going to see an important topic in semiconductors, that is its introduction. So we'll see the introduction to semiconductors. In this video we are going to see about the introduction to semiconductors, definition of semiconductors, types of semiconductors, and the concept of a whole we are going to discuss in detail. Bond and band structures of a semiconductors also we'll see, and we end this video with the definition of Fermi level. Firstly, we'll see the introduction part for this one. As we know all, certain substances like germanium, silicon, carbon, they're not good conductors like a copper and nor insulators like a glass. So in other words, its resistivity is about 10 power minus 4 ohm meter to 0.5 ohm meter. So it is in between. These materials lies between the conductors and insulators. The gap between the valency band and conduction band is small in these semiconductors. And we cannot imagine today's electronic world without these semiconductors. So they're extensively used in electronic circuits. If we observe the properties or difference between this in terms of a temperature and conductivity, if we concentrate on insulators, they have very low conductivity at low temperatures, and even at high temperature that shows a small conductivity. In case of conductors, as you increase the temperature, conductivity goes on decreases. But we can observe effective rise in the conductivity with the temperature in semiconductors, which makes a semiconductor is an important thing. Now come to the definition as we discussed before. In any material, if the energy gap is small, then it is called semiconductor as shown here. And the main important here, energy gap refers to the highest level of the valency band to the lowest energy of the conduction band. This is only called band gap or energy gap. And the speciality of this semiconductor is at low temperature it acts like an insulator, at high temperature it acts like a conductor, and at normal operating temperatures it acts like a semiconductor. So a semiconductor is acting like a insulator at low temperatures and conductor at high temperatures, which makes a semiconductor special from other. Now we'll see the semiconductor types. It has mainly two types: intrinsic semiconductor and extrinsic semiconductor. Intrinsic is nothing but a pure form of semiconductor. Here pure refers to no other element. Means if I say intrinsic germanium, in that crystal you are going to have only the germanium atoms, no other foreign atoms. All are germanium, no other atoms exist. It is a pure form, and that is called intrinsic semiconductor. Now come to extrinsic is an impure form of semiconductor. Means for a pure form we are going to dope with other elements. So then type depends on type of a doping, that will become either N-type semiconductor or P-type semiconductor, depends on doping. We will see in clear in the next slides. Now come to the concept of a hole. Hole is a same amount of positive energy equal to an electron but with opposite polarity. We know that electron is exists like this with a negative charge, and hole is the same amount but it is a positive charge, and their movements also different. In semiconductors, hole also carries a current. So in semiconductors, this unfilled covalent bonds were exist, and there only take it as a holes. These holes also constitute current in case of semiconductors. And the direction of hole current is same as conventional current but opposite to electron flow. Now we'll see in clear if I say this is a semiconductor and if you apply the electric field in this direction, then electrons are moving in the opposite direction as shown here. And current due to electrons are moving in the direction opposite to electrons, or I can say the current due to electrons is moving in the direction of electric field, and holes are moving in the direction of electric field, and current due to holes are moving in the direction of electric field. In simple, when we apply electric field in one direction, holes, current due to holes, current due to electrons are moving in the direction of the field. Only the electrons are moving in the opposite direction. These directions play a major role while we are studying the diodes, transistors, all these things. Now we'll see the bond and band structures of intrinsic semiconductor. Here in any semiconductor, the bond refers to the covalent bond between the atoms. Band is nothing but its valency band and conduction band, how they exist. These things we'll see for intrinsic first. If I take silicon or germanium, bond structure will be like this. Each silicon or germanium consists of 4 valence electrons for each atom. And all these 4 valence electrons are bonded with neighboring atom in terms of a covalent bond. So this one refers to covalent bond, that is sharing of electrons. So they will form a crystal by sharing neighboring electrons. So if we observe, this is the situation at T is equal to 0 Kelvin. All electrons here are bonded. So I can say no free electrons and no holes exist here. For this one, if we increase the temperature greater than 0, the bonds are broken up. Here, the bond is broken up at this point and electrons become free here. So you have one electron. Here, there is an absence of electron. This absence of electron only we will take it as a hole. Like this, if you go on increasing the temperature, like this many bonds are broken up and many electrons will become free and more holes gets created here. And this one is a band structure. This is the valency band of intrinsic semiconductor and this is the conduction band, and this dotted line refers to Fermi level. In this intrinsic, whatever it may be the temperature, always number of free electrons or concentration of free electrons is equal to concentration of holes. Now, if we take extrinsic semiconductor, means impure form of a semiconductor, that is p-type, we will see now. This is pure form, that is intrinsic, and this is the temperature 0 Kelvin. So all are bonded. Now for this, at this 0 Kelvin, if I dope with a trivalent impurity like a boron, then all are bonded like this. But as we are doping with a boron which is a trivalent, out of these three are bonded with the neighboring germanium, and one side there is a deficiency of electron called hole. So even at 0 Kelvin we have one hole exist, means one positive charge exists. For this one, if we increase the temperature, as we discussed before, more number of bonds were broken up and more holes gets generated and electrons will become free. But whatever it may be the temperature, always number of holes are more than number of electrons in this one. So holes are dominating. So it is called as p-type, means positive type semiconductor. And now if you see the band structure of this one, we have a valency band and conduction band. Along with that, we have an extra level called acceptor level present. This acceptor level is due to this doping of atoms, trivalent atoms you can say. Now, similarly, if we study about the n-type semiconductor, initially we are taking a intrinsic semiconductor and we kept that at 0 Kelvin and we are doping with pentavalent impurity. Penta means 5, means we are doping with 5 valence electron atoms to the host material like germanium. Now, if we add pentavalent impurity like As, out of 5, 4 are bonded with the neighboring germanium and one excess electron is there, that is a free electron. So at this point, I have one free electron, but I don't have any holes. For this, if we increase the temperature, more bonds are broken up and more free electrons you will get, and where the bond is broken, there the holes will be formed. But always here, number of electrons are more than number of holes. So electrons are dominating, negative is dominating, so it is taken as n-type semiconductor. Now in this one, see the band structure. Again, we have a valency band and conduction band. Here, more free electrons are exist, so they are ready to donate. So extra level is present called a donor level. These are the bond and band structure for p-type and n-type semiconductor. Now we'll see the Fermi level. In all these cases, Fermi level we used many times. How can we define this Fermi level? It is the highest energy level that an electron can occupy at absolute zero temperature is known as Fermi level. In general, the Fermi level lies in between the valency band and conduction band, and in some semiconductors its position varies with temperature. So this is the introduction for semiconductors. Now link for the write-up or a notes of this topic as given in the description. Happy learning. Like, share, comment and please subscribe my channel. If you have any doubt on any topics in physics, just comment it. Definitely I'll try to add that video. Thanks for watching. Please post your questions below. For more updates, subscribe to Physics Made Easy. Thank you very much.